The final topic for Module 6 is binomial distribution, sections 4 and 5 of this notebook. Now, this topic, binomial distribution, is something I'd really love to skip altogether, or at least cover it lightly so that it is recommended but not required. Just an optional topic, I mean. However, I can't do that. That's because our textbook author does not agree with me, and as a matter of fact, he's putting quite a bit of emphasis on binomial. And that's reflected on my math lab exercises. And if I do not cover it appropriately here, then of course, students will have a hard time going through all those my math lab exercises, and then they're not going to like me very much. So what choice do I have? We'll have to cover it. Whether I like it or not, here we go. Please be warned, we're going to start a topic that is rather computation intensive and tedious, elementary but tedious, and here's a real kicker, not useful and not important. Why are we doing this? Well, to tell the truth, that beats me, but that's the way our textbook is written and we have no choice. Let's do it. Binomial trial. Bi means two, so there's no surprise in starting with a trial with two possible outcomes. Success, failure, nothing else. That kind of trial is called Bernoulli trial, named after French mathematician Bernoulli. A binomial trial is an independent repetition of Bernoulli trial. For instance, toss a coin 10 times. We have success, failure, head or tail, and what is the probability for 7 head and consequently 3 tail out of 10 tosses. That kind of thing is binomial trial. Another example, roll a die 15 times, and ace is success and everything else is failure, and success probability is 1/6, and the failure probability in that case is going to be 1 minus p, so it's going to be 5/6 for rolling a die. And then what is the probability to get 4 aces out of that total 15 trials? That kind of thing is binomial trial, and that kind of counting is binomial random variable. Basically, we want exactly r successes out of total n trials, and that is binomial random variable. Whenever you have a random variable, then that generates probability mass function, and that formula is this one, and cumulative distribution function, and that formula is right here. Please note that this expression for the mass function is repeated right here inside this parenthesis, and then we are summing those up. So this is cumulative probability. One mass, another mass, another mass, another mass, and then adding all those accumulate all the way up to numerical value x or less. Alright, so much for theory, and let's go over to example problem. Here we go. An urn contains 5 red, 3 green, and 2 blue balls. Choose 20 balls with replacements, so it's with replacements, so we have independence. So n equals to 20 repetitions. What is the probability that you get exactly 5 blue balls? So 5 successes are equals to 5, and the probability for success is 2 out of 10. We have 2 blue balls out of total 10. And we have formula right here. So let's use it. Probability of 5 successes, and let me expand the font. Okay, that's good. Total 20 trials. Among them, 5 successes, and consequently 15 failures. So total success, failure, and then P is success probability, 2 out of 10, and that takes place 5 times, 5 successes, and the other 15 times I'm going to fail. All you have to do is to calculate this, and we have computer here, so let's ask Mathematica to do that. And here's the answer. About 0.17 for 17.5% or something like that. Okay, how about the next example? Let's talk about cumulative distribution function this time. And it is about probability that you get at most 5. So this is for exactly 5. And at most 5, we are talking about this. Probability x is less than or equal to 5. And that is probability x equals to 0 plus probability x equals to 1 plus the probability for x equals to 2 and so on. That's basically what we want. So how can we handle that? We did one computation here, and that was for this one. And repeat this kind of computation 5 more times. So 4 successes, 3 successes, 2 successes, all the way up to 0 successes. And we are going to get 6 numbers. Adding them all up, I'm going to get what I want. And, well, here we go. 0 successes, 1 success, and 2, 3, 4, and then 5 successes. And if you do all those right and add them all up, you're going to get this number, 0.80 something. I told you this is highly unpleasant, tedious computation. Elementary, but tedious. By the way, is everybody familiar with this factorial notation? What is this exclamation mark? N factorial is defined as n times n minus 1 times n minus 2 times and so on and so forth, all the way over to the last number. For example, what is 5 factorial? It is 5 times 4 times 3 times 2 times 1. That is, let's see, 4 times 3 is 12. 12 times 10, so 120. How about 6 factorial? That's 6 times 5, 4, 3, 2, 1, so times 5 factorial. So it's 6 times 120, and that's going to be 720. Well, okay, I gave up. That's all I can handle with my mental math. Anything beyond that, you'll have to use your calculator. As for this quantity that you have to calculate, this thing is called binomial coefficient, and Mathematica calculated like this. Binomial 20, k. I used r in my previous expression here, but here I'm using k. Well, I hope that doesn't matter too much to you because it's just choice of character. Or you can write like this as well, 20 factorial over k factorial over 20 minus k factorial, like those. If you use TI-80 level calculator, something like that, and this is not going to be too bad. You'll be able to calculate it. But still, it's tedious. You'll have to do this, total 6 times and adding them up. It's going to be time consuming. Now, here's a question. Why in the world are we doing this? In order to study EARN model better, in order to study rolling die? Actually, it has some importance in empirical question as well. Here we go. Suppose that the approval rate of the current president is 39% and the disapproval rate is 57%. The rest of the people did not answer, so these two numbers do not add up to 100%. But that's okay. We're going to get 39% and we're going to get 1 minus 39%. This result is based upon a poll result published by Gallup Institute on June 10, 2020. So this is actual figure, the real problems. I did not make up these numbers. Alright, based upon this actual data, real life data, let's do some math problem here. What is the probability that a third of 18 randomly selected people approves the president? Okay, 1/3 of 18, so we are talking about 6 out of 18, right? And at most 1/3, so 6 or less. So this is basically what we have to find out. So basically we want 0, 1, 2, 3, 4, 5 or 6 people approving the president. So we have to do this. And I don't want color anymore, so let's go back to black. Okay. And then for number of successes, 6 or less. Let me increase the font. Okay, so out of 18 people, 18 minus R, and then success probability is 0.39. Okay, 0.39. And then failure is 1 minus of that, of course. And then 18 minus R, that's gonna give me exactly R successes. And then sum them up. For R going to 0 to 6. And we get the probability. And this is the estimation. The next problem, we're talking about 12 people. So instead of 18, we have to use n equals to 12. And then half of 12, so okay, all right, I'll stop there. You can figure it out. And then we are talking about disapproval, so you have to use 57%, not this one. This one is for A, this one is for B. Well, I'll leave that to students. One final comment here. Now, compared with previous examples, this one is a bit more realistic, but still not realistic enough. Because who knows, I mean, who can tell that 39% and 57% are correct? They aren't. They're all estimations. And this one is based upon the assumption that these estimated probabilities are real probabilities, and then based upon that assumption, which is incorrect, we're selecting 18 people and doing the analysis. This is not realistic. The real problem is going backward. We do some sample study with, say, 2,000 people and get approval percentages there, and we want to infer the real approval rates based upon the sample study. And what kind of error do we get? That kind of thing is called inferential statistics, and that's something we're going to be doing in the latter half of this course. And that is really important and very, very realistic. Here's a problem though. When we are doing that, we do not use any of these. These binomial formulas are totally useless in real application problem. So why are we doing this? Well, that beats me. It's just that our textbook is written that way.